If we have extrema in multivariable that is three-dimensional, then how we can be assured that it is maxima or minima through algebraic? So that is the concept that we are pursuing. So one idea is that if I know that a point is a critical point in two dimensional, three-dimensional. How I can find if a point is critical, if a point is critical or not, then the first derivative we equate to zero, and then we get the independent variable value, and at that value then we know that fx or fxy is extreme point. So I go for first derivative. If it is two-dimensional, then fx. If it is three-dimensional, then fxy. Then if it is three-dimensional, then fxx. I mean, if it is three-dimensional, then fx means partial derivative along x-axis and fy partial derivative along y-axis. And then we set it to 0, whatever derivative comes, and both fx and fy, and we try to fetch the independent variable x and y value. Those values, if I see the fx, y or z, then at that point the z is kind of the it is extreme point in the sense that either it is maxima or it is minima or it is a saddle point, this side like this and other side like this. Either maxima, it neither maxima nor minima, or something that is undefined. Like case of cone, fxy equal to a square root of x square plus y square. Fx equal to x by a square root of x square plus y square. Fy equal to y by a square root of x square plus y square. If that is the case, then to find the critical point means, like if I have a surface, if I have a surface, okay, if I have a surface in any form, then along x-axis, if I see, if this is x-axis, this is y-axis, and this is z-axis, then if I have a surface, not the line, if I have a surface z value, then I get the differentiation along x-axis. How surface? If I cut the xz plane, then in xz plane, where is the maxima or minima? In YZ plane, if I make a cross section like this, and then in YZ plane, where is maxima or minima? If I find, then if I see the cone, then xy square root of x square y square. If x is 0, then for any y it becomes 0. Y by x square root of x square plus y square, if y is 0. So if x is 0, y is 0, then it is an extreme point because their derivative is 0. But if we see back again, then fx equal to x by square root of x square plus y square. If means fx equal to, whereas the actual function, 3D function is fxy. Fxy equal to square root of x square plus y square. So dfxy by dx, that is fx, is x by a square root of x square plus y square. If x is 0, y is 0, 0 by 0 means it is undefined. Fy is y by square root of x square plus y square. This means that 0 by 0 is undefined. So we can see that extreme point exists when the derivatives are either 0 or it is undefined. So whatever the case, extreme points, when we see the extreme point, there it can be maximum, it can be minimum, neither of them, that is another term, are undefined. So in cone is like this. Okay, if cone is like this, at this point, it is something that the differentiation is undefined. So if I say x equal to 0, y equal to 0, fxy equal to square root of x square plus y square. When x 0, y 0 means it is 0, defined. But dfx by dx, dfxy by dx, dfxy by dy, both are undefined there. So these are the cases. But anyway, if I know that it is minima, if I know it is maxima, then if it is two-dimensional, then through dual derivative, I can find it is minima or maxima, like sine t. If sine t is a function, then y equal to sine t. If I take a if I take an open region, okay, not closed region, if I take an open region in a sense, or rather I say a bounded region, not a closed region. So between minus pi to pi, exclude minus pi and take a region in between, and then find then what is extreme point. So there is only one extreme point, that there, I believe there are two extreme points. One is at minus pi by 2 and another is at pi by 2. So it is maxima or minima. So what we saw, that if I take double differentiation and if it is positive, then it is minima. If it is negative, then it is maxima. So this is what we have seen, that through algebra only I can find it is minima or maxima. Otherwise, if I know, like if I have sine t and if I differentiate, it becomes cos t. To get the extreme point, cos t should be 0. Then t should be pi by 2 or minus pi by 2. At that point, now if we go back to the equation sine t, then at pi by 2, what is the value of sine t? That is 1. Prior to pi by 2 means around 80 degree or 100 degree. There I will try to find the y, ft. Okay. And if it is less than 1, means that is maxima. Same as minima. If it is more than that, then it is minima. Now we went for second derivative and we saw the second derivative of any function that is maxima. Then left side and right side. Left side the slope is positive, right side slope is negative. So differentiation is like this. If this is x-axis and this is y-axis, then differentiation is positive. Near to origin, it intersect x-axis and go negative. That is the slope. So near origin, near the extreme point, the slope is negative, means double differentiation is negative for maxima. Similarly, for minima, it is from negative side, crosses the x-axis and it go positive. So when it is crosses the x-axis, means where it is the extreme point, there the slope is positive. So double derivative is positive for the minima. Okay, but these things will not work for the multivariable case, where we have two independent variables x and y. Double derivative doesn't mean fxx. Double derivative is fxy also. dfxy by dx, dfxy by dy, fx, fy. Or double derivative is fyy also. So there are three double derivative as far as two independent component multivariable case is concerned. Okay, so we cannot blindly say that I calculate a multivariable and it is positive or negative. Then I can find what is the scenario. So that we cannot do. Now we went ahead and then we kind of took example of how I can estimate a curve, how I can estimate a kind of, if I take two-dimensional line equation, then line can be straight line or line can be curve also. If it is a straight line, then how any line, either it is a straight line or curve, can I represent it in differential way? This is what the approach we were talking about. If line is y, if there is a line and if I calculate dy by dx on the line, then I can have exactly same line if I have another algebraic equation y equal to dy by dx into x, where dy by dx value is the place where any point on the line. Okay. Now, if I take if I have independent variable as t and dependent variable as y, then y equal to ft. If I take any point at t0, then dy by dt at t0. So new equation, we can reproduce the line, whatever the line I have. I can exactly reproduce the line with equation of y equal to dy by dt at t equal to t0 into t. Okay, if I thinking about shifting of the line not passing through origin, then y minus y0 equal to dy by dt t at t0 into x, or y equal to y0 plus dy by dt into t. Okay, so this is the kind of we reproduce single straight line through the differential equation. If it is a kind of if it is a polynomial equation, if I have a line and its equation is y equal to t square, y equal to t square, then I have to do double differentiation. Then I can have, if ft equal to t square, then I can have another function gt equal to d2y by dt square, d2y by dt square into t square. Okay, so if it is t square, y equal to t square is ft, then dft by dt is 2t. Okay, so if 2t, d2y by dt square is 2, constant 2. If that is the case, then if I have another function gt that is in form of differential equation, then d2y by dt square into t square, d2y by dt square into t square is the new same equation in differential form. So d2y by dt square is 2. So 2 into t square, whereas I had original function as t square. So I have to divide it by 2. If it is t to the power 4, then d4 d4y by dt to the power 4. This one I have to calculate because t is in power 4. So ft equal to t to the power 4 means d4y by dt 4 I have to calculate. So it will become 4 into 3 into 2. That's it. So first derivative is 3t is 4t cube. Then another derivative is 4 into t is 4 into 3 t square. Then 4 into 3 into 2 t to the power 1. And then 4 into 3 into 2 into 1. That's it. So it turns up to factorial of 4. So if I have a ft equation y equal to ft equal to t to the power 4, and if I want to get the same equation through algebraic equation, through the differential equation in algebraic form, then there is a gt. So y equal to gt equal to, then it is d to the power 4y, d4y by dt4 into t to the power 4 divided by factorial of 4. Okay, so now the numerator is 4 into 3 into 2 into 1 into t to the power 4, denominator is factorial 4, so it will come back to t to the power 4. So the idea is that if I have any equation of line that is kind of a curve or a straight line, I can reproduce it exactly like that through the differential equation. So if I have equation of a line ft equal to t to the power n, then I can reproduce it back through the differential equation gt equal to d to the power ny by dt to the power n into t to the power n divided by factorial n. Okay, so I can reproduce any line, either it is straight line or curve, through differential equation by like this. So if I have the polynomial equation of a line, and that equation is t to the power n, then n times I have to calculate the derivative, and then dny by dt n into t to the power n whole divided by factorial n would be the exact reproduction of the polynomial to the differential algebraic equation. This is what we saw. Now, if I have a polynomial equation in the power of n, where n is very high, higher than 10, 20, 30, if that is the case, then can I represent it with the polynomial, with the differential equation of power 1 only, not to the power n? Okay, that is okay. Then I can say gt equal to dy by dt into t. Gt equal to dy by dt into t. I am not taking a offset into the consideration. All line are passing through origin. If you want offset, then you can add y0. So y equal to y0 plus dy by dt into t. So I am removing y0. So y equal to dy by dt into t is a line where dy by dt is the first level derivative of the actual equation ft, that is in power t in power of 10 in power of n, like t equal to t square plus t square plus t to the power 6 plus I am removing coefficients and sign plus t to the power 12, something like that. That is the ft. Then if I calculate dy by dt and t I replace at any point independent variable t equal to t0. ft y equal to ft equal to t plus t square plus t cube plus t to the power 6 t2 plus t to the power 12 t to the power 20. Then dy by dt I am going to calculate, and then whatever comes, then t I'll replace with a scalar value t0. So I get a dy by dt as a scalar value. Now I have another equation of a straight line through differential equation algebra, that is gt equal to dy by dt. So dy by dt at t equal to t0 is scalar value into t. Now it is a straight line. So if I have a curve like this and then I have a straight line, if I have a curve like this, that is ft, and then I have a straight line that is gt, then both are different. They do not match. If I have a curve like anything and I have a differential equation line, but when t equal to t0, at that point they touch each other. So I can say that I can represent any curve through a fictitious straight line where they are same at point t equal to t0. This is what we saw. Suppose I have a curve that is in power of 20, but it is a mixture, t equal to t square plus t3 plus t to the power 6, t to the power 9, t to the power 12 plus t to the power 20. If I take 20th derivative, d20y by d20 power 20, and then at point t equal to t0, if I calculate the d20y by d20, then I can have another curve as gt equal to d20y by d20, d20y by dt power 20 into t to the power 20 divided by factorial 20. Now the whatever we are getting gt is also a curve. ft is a curve, gt is also a curve, and it is matching the curve. It would not do the exact matching, but it would match. It is far better than a straight line. Okay, so that is the situation. Now I can see that if I have a polynomial equation, and that is mixture of all the kind of power, t to the power 1, t to the power 2, t to the power 3, like this, if it is only one, either t to the power 10, t to the power 5, t to the power 12, if it is in that form, then I can do that much. Like if ft equal to t to the power n, then dny by dtn, if I take that much derivative and I calculate it at t equal to t0, exactly I can reproduce through differential equation where gt equal to dny by dtn into t to the power n divided by factorial n. These things are not available in any of them. This is something that we will file disclosure on. Okay, so estimation of any curve through differential equation is available, but this explanation is not available. This is straightforward and very simple. Now, if I have a polynomial equation in any form, combination of all the kind of power of the t, then what would be the estimation? What is the approximation of the differential equation? Then very straightforward answer is that I can add everything. So now we have dy by dt into t, divided by factorial 1 plus d2y by dt square at where it is at t point t equal to t0 into t square divided by factorial of 2 plus d3y by dt cube where this differentiation, triple differentiation, is at point t equal to t0 into t to the power 3 by factorial 3 plus d to the power 4 y by dt4 at t equal to t0 into t to the power 4 by factorial 4. Keep adding it till you go. So till you go in the sense that if I have polynomial equation where maximum the power is n, then maximum I can go till n only. Beyond that it will be 0, 0, 0. Okay. So for any polynomial equation ft, then the approximation of ft in gt as far as differential equation is concerned, then we can say that ft0. So any line equation, if we see, then it starts with y minus y0 equal to mx. Y minus y0 equal to mx, where that curve we have shifted y0 along the y-axis. Or if I know that it is passing through point x0, y0, then y minus y0 equal to m x minus x, whatever is comes in the empirical or practical form. So if I say I shift along y-axis y0, then at that x0 is 0. It is passing through a point that is 0 comma y0. Then anyway y minus y0 equal to m x minus x0. So x0 is 0 and then y minus. So if I take that case, then y0 is nothing but what is the value of the function ft when t equal to 0. So I can say now y equal to ft0, f at t0, because y minus y0, y minus y0, if go that side of the equation, it becomes positive. So y equal to y0 plus mx. So y equal to f at t0 plus, now we will repeat the story. Now we have dy by dt at t equal to t0 into t by factorial of 1 plus d2y by dt square into t square by factorial of 2, where dy by dt is a scalar value, d2y by dt square is a scalar value taken at t equal to t0 plus d3y by dt cube into t cube whole divided by factorial of 3 plus d to the plus dot 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 d to the power ny by dtn into t to the power n divided by factorial of n, where d to the power ny by dt to the power n is calculated at t equal to t0. So that is a scalar. If I get this equation, this is roughly approximation of any polynomial equation ft, where the maximum exponent, where maximum power of the t is n. If I have ft equal to t plus t square plus t to the power 6 plus this, I am excluding minus plus and coefficient and scalar value. Then if maximum is t to the power n, then the ft equation can be approximated with another equation gt in differential form. Okay, then it will be f t0, f at t0 plus dy by dt when it is t, when dy by dt is calculated as scalar when t equal to t0 into t by factorial 1 plus d2y by dt square into t square by factorial 2 plus dt3 by dt cube into t cube by factorial 3 plus d24 by dt4 d24y by dt4 t to the power 4 divided by factorial 4 till is go till dny by dtn n power n into t to the power n by factorial n. So that is the approximation of ft as GT. Now we'll come to our the original signs. So original signs what we have now is, can we now approximate any function as parabolic function? Okay, so parabolic function, in a sense that parabolic function has very peculiar nature. Parabolic function has only one extreme point, that is guaranteed. Okay, there is no other extreme point, only one extreme point. Either it can be minimum or it can be maximum. Okay, so if I have parabolic equation y equal to kx square, if k, I don't need to do any derivative. If k is positive, then it is global minima. If k is negative, then it is global maximum. So any equation, if I'm able to do a approximation equation in the form of a parabolic equation, then looking at k, quickly I can say that at that point, if I have calculated extrema points, then at those points, extrema point t equal to t0. You remember that when we are doing ft and gt mapping, then we are calculating all the differentiation at t equal to t0, where t0 is now our extreme point where derivatives are zero. There is no slope. So if there is a curve like this, then at these points, the slope, the dy by dx or dy by dt is zero, means this is parallel to x-axis. At those extrema points, okay, those are the points I say t equal to t0. So at those extrema points t equal to t0, then I have to calculate that it is maxima or minima. So around that point, whatever the equation I have, the ft, I transform it into gt, that is a parabolic equation. If I know it is a parabolic equation, just see the coefficient of parabolic equation and quickly you can say that it is maxima or minima. Now if I have any ft, then approximation of the ft into gt up to power of 2 1. This is what we'll see, not beyond that. Okay, so up to power, this much approximation we are doing. So if gt, then gt equal to f t0 at t0, gt equal to f at t0, not ft, f at t0, where t0 is the point of the extrema, plus dy by dt at t equal to t0 into t, plus d2y by dt square into t square by factorial of 2. So I have now another equation. If ft is an equation of polynomial, then I have another equation as gt. If another equation is gt, then formulation of the gt is y minus y0 equal to mx. I mean, this is the basic formula. Minus y0 on goes on that side, it becomes y equal to y0 plus mx. Now y0 is nothing but a point on y-axis where independent component t is 0. So, okay, that is the y0. Now, we are calculating the curve. So in the curve we have the y value when t equal to t0. If that is the case, t equal to t0. If that is the case, then net equation would be gt equal to f t0. gt equal to f t0 plus dy by dt at t equal to t0, t minus t0. Now this is complete equation, because when we see the actual equation of the differential estimation, then it is y minus y0 equal to mx minus x0. Then here, if I take x0 as t0, then y is f t0, f at t0. But if I take t0 as 0, then it is interception on the y-axis. But now we are talking about extrema. Extrema means extrema can happen, the extreme point where the dy by dx is 0, where slope is 0, can happen at any independent variable t equal to t0, not it is only at t equal to 0. So in that case, I have will take formulation in the form of y minus y0 equal to m x minus x0 in bracket x minus x0. If that is the case, then if I have the original polynomial equation as ft, then I have differential approximation of ft as gt. If that is the case, then gt equal to ft0 plus dy by dt, t at t0, dy by dt into t bracket t minus t0 divided by factorial of 1 plus d2y by dt square, where the it is calculated, the derivative is calculated at is a scalar value and calculated at t equal to t0. So d2y by dt square into in bracket t minus t0 whole square divided by factorial of 2. So up to here only we will do the approximation. Now if I proceed again, then we see that gt equal to ft0, gt equal to ft0 plus dy by dt. So dy by dt is 0 at extreme point. So that factor, the first factor where t to the power 1 is there, that is gone. Now I have gt equal to ft0 plus d2y by dt square at t equal to t0. So ft0 plus d2y by dt square into t minus t0 whole square divided by factorial of 2. Okay, so nice it is. Now if I move on, then it becomes gt equal to f t0 plus d2y by dt square into t minus t0 whole square by 2. Okay, if I see ft0, then it is a constant. It's just moving some algebraic equation one place to another place. That's it. It has this constant has no other name. But the main equation is d2y by dt square, that is d2y by dt square divided by 2 into in bracket t minus t0 whole square. This is parabola. This is parabola where t minus t0 whole square means it is shifted, the parabola is shifted along x-axis t0. If it is y, if gt equal to ft0 plus d2y by dt square divided by 2 into t minus t0 whole square, then it is same parabola as it is centered along the origin. Now it is shifted t0 along the x-axis and it is shifted ft0 along the y-axis. That's it. So it came in a formulation of y equal to kx square. Now only thing I have to find, because t minus t0 whole square has no sign, it is always positive. So main thing that I have to find is d2y by dt square at t equal to t0 divided by 2. What is the sign? And I can say it is maxima or minima. Okay. Now if I take y equal to sine t, y equal to sine t is a ft equal to sine t. Now I have to find, now if I differentiate, it becomes cos t. If I equate it to 0, then t equal to pi by 2 and minus pi by 2. In a open region or in a bounded region, minus pi to pi, where minus pi and pi are excluded. Then in that region, I have two extrema, pi by 2 and minus pi by 2, where the derivative of sine t, that is cos t, is 0. Now I have to find pi t, pi by 2 and minus pi by 2, the extrema is maxima or minimum. Now I have gt, I have ft equal to sine t, then ft equal to sine t, that is transformed into differential equation gt. So gt equal to ft0. So t0 first we will calculate at pi by 2. So f pi by 2. So f pi by 2 means sine pi by 2, that is 1. So 1 plus d2y by dt square. So sine t derivative is cos t and again derivative is minus sine t. So minus sine t into t minus t0 whole square divided by 2. So minus sine t by 2 is the coefficient of a parabola where now t minus t0 whole square. So t minus pi by 2 whole square. I don't worry about it. I worry only about the coefficient, that is minus sine t divided minus sine t. So minus sine t at t equal to t0. So that is minus 1. So minus t equal to pi by 2. So minus 1 by 2. So minus 1 by 2 is the coefficient of the parabola. Since it is negative, then it is maxima. So if y equal to sine t at t equal to pi by 2, then it is maxima. Now we will calculate at minus pi by 2. So now we have gt equal to ft0 plus d2y by dt square into t minus t0 whole square divided by 2. If it is parabolic equation, then gt equal to ft0 plus d2y by dt square at t equal to t0 divided by 2 into t minus t0 whole square, where the coefficient is d2y by dt square at t equal to t0 by 2. So I am worrying about the coefficient of the parabola. So dual derivative is minus sine t. Sine t cos t again minus sine t. Sine t at minus pi by 2 is minus 1. So minus sine t becomes plus 1. Plus 1 by 2 is the coefficient of the new parabola. If that is the case, then plus means it is minima. Okay. So if I have ft equation y equal to sine t, then minus pi by 2 is the extrema plus pi by 2 is the extrema. Then at minus pi by 2 it is minimum, because the transformed equation ft is sine t is the original equation. The transformed equation gt in parabolic shape is there, where m equal y equal to kx square. The k, the coefficient of the parabola, happens to be 1 by 2. So at minus pi by 2 coefficient is 1 by 2, whereas plus pi by 2 coefficient is minus 1 by 2. So if it is minus, means that is maxima, and minus pi by 2 it is plus coefficient, then it is minima. So nice. Any algebraic equation I can take and I can do dual derivative, and then I can transform into algebraic equation, the differential algebraic equation, and that is parabolic in the shape, and then simply I calculate the kx square form, and sine of k would tell us it is maxima or minima. Now what is the kind of more idea? Okay, so more idea is, now we will move to multivariable case. So in multivariable case we have two variables x and y. So earlier we had ft or fx as function. Now I have function as fxy. So two independent variables fxy. If it is fxy, then what would be the situation? So I have now the polynomial equation in two independent variables x and y. So it can be like y to the power 3 plus x into plus 25x into y minus x to the power 4 minus y to the power 2 plus x square x to the power 6 into y to the power 6, like any polynomial equation in the independent variable of x and y. Okay, now ft is transformed from 2D to 3D in fxy. Fxy is polynomial equation where the maximum power of x is n and maximum power of y is m and n. X can take any power, y can take any power. Okay, what is maximum among them? That we have seen. Consider that both are n to the power n. Now if I have a, earlier I had a, if it is 2D, then I have a curve. If it is 2D, then I have a curve. Curve can be a straight line or curve can be curve. But if it is 3D, then the line, the curve is transformed into surface. If it is surface, then it can be either a straight surface or surface can be like this also. Okay, so surface, if I see along x-axis, this is x-axis, this is y-axis, and this is z-axis, then each point in along in xy plane, they transformed into z value. If I connect all the z value, I get a surface that is 3D. All along I get a volume. But if I connect the z values against each xy plane in xy plane, I get a z value. If I connect all the z value, I get a surface. Surface can be a straight line, a straight surface, flat surface, or it can be like a curved surface. Both is possible. If it is a straight line, then it is a monomial surface. That is, it is in form of x to the power 1 and y to the power 1. So if I take ft equal to x plus 1, that is the simplest case. Xt equal to x plus 1. Then what is gt? In the formation of in the formation of differential equation, then what can be the gt? If ft is x plus 1, monomial surface, then means flat surface, then what is the flat surface approximation as far as differential equation is concerned? If I had a 2D, then I had ft as t to the power 1. Then gt maximum I can go t to the power 1 only. Beyond that, if I go, then d2y by dt square would become 0. So here also, if I have a polynomial surface, if I have a monomial surface, a straight surface, flat surface, ft equal to x plus y, then maximum approximation gt I can go power of 1. So if I do the partial derivative, then maximum I can do dz. Now z equal to fxy, that is x plus y. So dz by dx. If I do d2z by dx square, then complete 0. d2 dy by dz. If I do d2y by dz, then complete 0. If I do dz by dx, dz by dy, dz by dx and dz by dy complete 0. So maximum I can do partial derivative along x-axis and partial derivative along y-axis, dz by dx and dz by dy. If that is the case, then the approximation algebraic differential equation, that is gxy, would become fx0y0, where the surface is calculated at the value x0. So it is same as line that I have initial surface that passed through the origin. That surface has formulation. That surface has formulation in differential equation as z equal to dz by dx into x plus dz by dy into y. Earlier we had y equal to dy by dx into x, y equal to mx. Here z equal to mx plus ny, z equal to m1x plus m2y, whatever. Okay, where m1 is dz by dx, m2 is dz by dy. What is the rate of change along x-axis? That rate of change, if I multiply by x, I get the z value. What is rate of change along y-axis? If I multiply that rate of change with the y, then I get vertical along z-axis. If I add these two, then net z I get. That is z equal to dz by dx into z plus dz by dy into y. Dz by dx into x plus dz by dy into y. Dz by dx is rate of change in z seen per unit change in x. If rate of change I know, if I multiply by x, I get the vertical. Dz by dy, rate of change I know, if I multiply by y, I get the vertical. If I add these two vertical, I get the net vertical. If I have a surface like this, surface is going down along x-axis, but surface is going up along y-axis. So the net surface is like this, like this. So if I see along x-axis, it is going down, but if I see along y-axis, then it is coming up. Y-axis it is coming up, whereas x-axis. So this is a surface that is dz by dx is negative. In that sense, if I multiply by x, means positive side, z will go down. Then dz by dy is positive. Then if I multiply with that, it will give vertical up. Which is more, dz by dx into x is more or dz by dy y is more? If dz by dy into y is more, then if I calculate from the origin, the net z I'll get little up. If dz by dx into x is more, then after calculation net z I'll get down. So that is the net surface calculation as far as differential algebraic equation is concerned, that is gxy. From fxy, I am doing approximation in gxy. So gxy equal to fx0y0. F calculates. Now, whatever the surface we are talking about, it is passing from the origin. If I am shifting it to any point, passing through any point x0, y0, x0, y0. If it is passing through a point, okay, x0, y0, whatever z0 comes into the picture. If at x0, y0 is a point on xy plane for which I have z as z0. If it is touching the z0 where x and y is 0, then it is passing through point 0, 0, z0 or any point x0, y0, z0. If that is the case, then if I approximate gxy, that is z equal to gxy, then z equal to gxy equal to equal to fx0 y0, that is z0, plus dy dz by dx, where dz by dx is calculated at x equal to x0 into x factorial 1, plus dz by dy calculated at y equal to y0 into y by factorial 1, and dz by dx into dz by dy I can't do because it becomes 0. So for the linear surface, so we have the algebraic differential equation is z minus z0 equal to m, means dz by dx into x minus x0 plus dz by dy y minus y0. If that is the case, then our equation would become here gxy equal to f x0 y0, because z0 would go that side, f0 f x0 y0 plus dz by dx into x minus x0 divided by factorial 1 plus dz by dy into y minus y0 divided by factorial 1. Now, this is equation of a linear surface into differential linear surface. Now, they would be exactly same. Okay, what about polynomial? So, I believe it is too much. So, polynomial is in form of, if it is in form of x plus y to the power 1, if it fxy, it is in surface form, then if surface is curved, then it will be in form of x plus y to the power n. So we will see first x plus y to the power 2, 3, 4 and to the power n, and then what would be the gxy approximation of the curved surface, and then we will move ahead to find that our extrema is maximum or minimum with the differentiation. Otherwise, we were calculating the fxx, fyy and fx and fy, for dz by dx and dz by dy, equating it to 0 and then finding the point x0, y0 where it is extreme point. Then we were drawing contour lines, and in the contour line centered at x0, y0, we were seeing all around all the contours that they should be of the same sign. If contour is one side it is positive and other side it is negative, then that is a saddle point. Or if the if that fx and fy all together at x0, y0 is undefined, then it is neither maximum nor minimum, it is undefined. If it is a saddle point, then it is neither maxima nor minima. Otherwise, if contours are of same sign and from the x0 y0 point the around contour are growing, then it is minima, a contour are going down, then it is maxima. So first fx and fy partial derivative we calculated, that is machine work, means machine would calculate the fx and fy, but beyond that human work, that we have to draw the contour and then we go back Means we go back to the original fxy equation and we see the contours at any point x and y around x0, y0, and then we see the contours all direction, it is of same sign. Then we see it is maxima, it is minima, neither maxima nor minima, or the extreme point is undefined. We don't know. We don't know. I know it is extreme point, but definition is undefined. So machine work and human work. The main idea was to transform the human work completely to the machine work. So machine will calculate now that these extreme points are what. So from the 2D now we have come to 3D, and ft to gt, now it is fxy to gxy. For monomial we have calculated the gxy from fxy gxy, that is gxy equal to fx0 y0 plus dz by dx into x minus x0 divided by factorial of 1 plus dz by dy into y minus y0 divided by factorial of 1. So beginning was fx0 y0, that is z0. Anyway, so we will proceed on that and then we will know through everything through from the machine perspective. That will